Okay, so we are going to be looking at conditional probability and tree diagrams. The nice thing about what we are covering in this first half of Unit 4 is it's all very similar to what you've seen before. So, not seen formally, but you've kind of experienced it in other math classes. So, we've talked about the general addition rule, we've talked about the general multiplication rule, we've talked about when we can find things that are um, disjoint where they're mutually exclusive. Now we're going to go into conditional probabilities. So, in previous notes, we've assumed that the events do not influence each other, which are independent events. Some examples of these include some coins. When we flip a coin, does not influence each other. When we spin a spinner, when we roll a die, all of those things are independent events. But what happens if they do influence each other? So then we are going into more real world probabilities, and they can be a lot trickier to navigate. And we like to call these things conditional probabilities because the probability that one event will happen if it is known another event has happened. So something occurring to begin with influences the probability coming up. And the notation that we have for conditional probability is probability of A given, and given is this line right here. It's a bar. Most of the time on your keyboard, it's right underneath the backspace button with your forward slash bar B, where the bar symbol means given. So a lot of the probability language in this unit is like its own language. So every time we see the bar, you should be reading it as given. So probability of A given B is read as the probability A occurs given that B has already occurred. So every time you read these, the second statement, sometimes it's BA. Whenever you have the second statement, that's the event that has already happened. So that's the given that this has occurred. Now, the formula for conditional probability is there's two ways to write it depending on what direction you're going. Again, your A and B events could be completely different. The probability of A given B is equal to the probability of A. And remember, this symbol here represents and, probability of A and B over the probability of B. And notice here that my given statement is my denominator. Or we have the probability of B given A is equal to the probability of A and B. And notice again, I have my given statement is my denominator. Now, this is one of the formulas on your formula chart. We will take some time before the AP exam, once we get our units wrapped up, to go over what do you need to remember for the AP exam and what will they give to you. For now, everything we do in here is open notes in terms of testing. So as long as you have your notes handy, you will have this formula with you. So why does this formula work? Well, when you know something has happened, that's going to change the sample space. And remember, the sample space is typically the entire square. Now, when I have a given, it's going to shrink to the given event. So the probability of A given B, if you know that B has occurred, the sample space is no longer this entire box. It's no longer S. It shrinks. It shrinks to the given statement. And it shrinks to be the circle of B. So now I'm no longer the entire box S. I'm now just the circle B. So that changes the denominator of my probability. Now, if I want to know what's happening with event A given that I already have, let's kind of color coordinate. I know which one I picked for this. If I want to get A, I have to go in and look at my new sample space of B and see where else do I have A. And that's going to be the intersection. This intersection is the probability of A given that B has already occurred. So, looking back at that formula that we have up top, the size of the other non-given event becomes the intersection. That's this highlighted portion in the middle. And the size of the sample space becomes the given event. So basically, we are shrinking our sample space from one entire population to a subset of that population. And the subset of that population becomes my denominator, and then whatever you're interested in occurring becomes your numerator based on that subset. So this is kind of why the given conditional probability works in terms of seeing it in a Venn diagram. Now that we have kind of seen how it works, we're going to go in and we are going to actually use it in order to kind of manipulate one of our rules we've already talked about. So I'm going to give you about a minute or so just for those of us catching up, writing down. Okay, let's go ahead and look at the multiplication rule for dependent events. So once we have the conditional probability formula, we can rearrange it into a new formula for finding the intersection of two events. So I have the probability of A given B, this is just the formula we had on the previous page, is equal to the probability of A and B over the probability of B. Now, if I wanted to use this formula to get multiplication rule, and remember multiplication rule is that and statement. And. So I'm going to go on both sides of the equation and multiply by the probability of B. What's going to happen is this denominator and this probability of B are going to cancel each other out, which leaves us with, if I were to convert this into a nice formula, probability of A and B is equal to the probability of B times the probability of A and B. Oh, sorry. One small error here. Should be probability of A given B. Let's see. Small error. At least I caught it now and not during seventh period. And we like to call this the multiplication rule for dependent events. So we have one for independent events, and that's just the probability of A times the probability of B. But when you have events that change based on one event occurring already, you are going to want to go with this formula. Now let's go ahead and actually use it. So use the two-way table below to calculate the indicated probabilities. So we have hair color and we have eye color. And for the first problem, they want us to know if we select a woman and find she has brown hair, so this is going to be our given statement, what is the probability that she will also have hazel eyes? So remember, we are going to want to have some type of probability statement accompanying our work. So I'm going to have the probability of hazel eyes given that she has brown hair. And all I'm going to do is take this statement and I'm going to use the formula for conditional probability. So that states that the probability of hazel eyes and brown hair is all over. And remember, your denominator is going to match the given portion of your probability statement. So hazel eyes and brown hair over brown hair. Now, all I have to do now is go to my table. So the probability that she has hazel eyes and brown hair. So I'm going to go to hazel eyes. I'm going to go to brown hair. That's a count of 29. So I'm going to have 29 over the probability that she has brown hair. That's going to be 143. So 29 over 143. If I plug that into my calculator, I get 0.2028 as my answer. And you may notice that I used counts rather than probabilities. Well, that's because they are the same. So if I were to turn this into probabilities, I would get 29 over 313 over 143 over 313. And basically what happens is you end up canceling out your denominators and you get 29 over 143. It doesn't hurt to do it this way. It just is an extra step that you have to be careful of when you're entering it into your calculator. You can just deal with counts only. And 313 comes from my total sample space of all of the women. I'm going to assume women? Yes, women who were surveyed. So we have one conditional probability down. Now we're going to look at if we select a woman and find that she has brown eyes, what is the probability that she also has black hair? So we have a given statement. The given this time is that she has brown eyes, and we want to see if I change my sample space to be only women with brown eyes, what's the probability of me then selecting someone who has black hair? So I'm going to do probability of black hair given that she has brown eyes. So I'm going to write my probability statement, black hair and brown eyes over the probability of brown eyes. And again, I have my denominator matching my given statement. So let's go ahead and look back at our table. So the probability that she has brown hair and brown eyes, or black hair and brown eyes, sorry, is 36. And the probability that she has brown eyes is 122. So I'm going to get 36 over 122, which is approximately 0.2951. And all I'm doing is entering these into my calculator. If your calculator is still giving you fractions, you can always hit the math button. They should have a decimal option for you to convert it to decimal form. General rule of thumb I say is rounding to 4 decimals is absolutely fine. Anything less and anything towards whole numbers gets a little iffy, especially because you're kind of losing a lot in that rounding error. I will always recommend at least 4 decimal places. And on tests and quizzes, I will be kind of specific, especially for probabilities, because I know we can get a variety of answers when we start rounding. Okay, so we have used the conditional probability formula. Now we are going to go on and talk about how can we use this to help us show independence. Because a lot of the time it's really hard to decide if 2 events are independent or not. So we will go the formula route versus just assuming independence as we did in our inference testing. So first, I have 2 things that I want you to recall. For independent events, the probability of A and B was just probability of A times probability of B. This is what we talked about in the last set of notes. And our conditional probability formula that we just used was probability of A given B is equal to probability of A and B over probability of B. Well, if my events are independent, if they have no influence on each other, then the formula for probability of A and B should fit here. So I'm going to substitute. I'm going to take probability of A times probability of B, and I'm going to substitute it in for this and statement. Because if I substitute it in and this entire thing ends up being true, then they are independent events. So I substituted in probability of A given B is equal to the probability of A times the probability of B all over probability of B. And we can make this a little bit nicer. We can make it easier on ourselves. So what I'm going to do is I'm going to, one second, I'm going to go ahead and cross out some things. So I have A times B all over B. Well, I have in the top and bottom the same statement, and I have multiplication. So I can go ahead and cross these two things out, leaving me with probability of A given B is equal to the probability of A. So to show or justify independence between two events, you're going to want to prove this statement. This is going to mean even though B has occurred, even though it happened, it had no impact. And that's the important thing. It did not change the probability of A. They are still equal to each other. That indicates that we have independent events. So if this ends up being true, they're going to be independent. If it ends up being false, they're going to be not independent. So basically, if you can prove that these two things are equal to each other, you have independence. Now, this is one thing that I know for sure is not on the formula chart. However, it is something that we can derive from things that are given to us on the formula chart. So they give us both of these statements, and we can use this to derive an independence formula by plugging in what we already know. So now we are going to move on and we are going to actually verify that we have independence for another set of events. So I'm going to give you a little bit of time to copy down. And the big key takeaway from this is knowing that this is the formula that we're checking from. Never on the AP exam, as far as I've seen, will they ask you to derive this formula and prove how it works. It's not that kind of class. It's just taking this and proving it for a different circumstance. So I'm going to go ahead and move on to our third page. The U.S. Center for National Health Statistics compiled information about injuries in the U.S., and the frequencies in millions are given in the table below. So I have a table where we know gender and we know the circumstance of their injury. And my first question asks, are the events female and home circumstance independent? So I'm trying to prove the probability of female given that they had a home injury is equal to the probability of female. And you could flip this. You could have done probability of home given female is equal to probability of home. Either way, it should work. If it's true, it's going to work for both. If it's false, it's going to fail for both. So given that piece of information, it does not matter which order you pick. And remember, we're just trying to see if these are equal to each other, because that's going to mean the probability of my second event has no impact on the probability of my first. So I'm going to go ahead and work with this first given statement to begin with. So the probability of female and home over the probability of home injury is equal to, well, if I go to my table, the probability of being female and having a home injury was 11.6, and the probability of having a home injury was 21.4. So I did 11.6 over 21.4 is equal to 0.5421. Now I'm going to go in and find the probability of being a female. So all I have to do is go and take my female total, which is 25.8, over the entire sample space because I don't have any given statement. I don't have any restriction occurring. And that gives me 0.4202. Now, when I look at these two values, 0.5421 and 0.4202, they are not the same. So because they are not the same, female and home injury are not independent. If they were the same, we would say they are independent. And we're not going to go into saying dependent because we don't necessarily know for sure that one is depending on the other and that we don't have any outside factors. So all that we can assume is that they are not independent. It's a weird stats thing that they like to do. They like to be nitpicky about. Now, part B of this question does not necessarily have to do with our table, but it does have to do with our rule for independence. So if the probability of A is equal to 0.44 and the probability of B is equal to 0.22, and A and B are independent. So if A and B are independent, then the probability of A and B is equal to A times B. What is the probability of A or B? So we're pulling in a lot of different rules here because remember, from 4.1, we have a formula for finding the probability of A or B. That formula is probability of A or B is equal to probability of A plus probability of B minus the probability of A and B. And we are claiming that they are independent. So because we have this claim, we're saying that this formula is going to work. So I'm going to take what I know, 0.44 and 0.22, and I'm going to plug it into this equation. So I'm going to get 0.44 plus 0.22 minus, using this formula, A times B, 0.44 times 0.22. So all I did was take this piece of the formula and plug it in for my AND statement, which is going to equal 0.5632. I will say a lot of the times we do see things like this on the AP exam where they ask you to kind of interpret and rearrange things based on given information. This could be a very, very common problem that pops up in the multiple choice section. So my final answer would be 0.5632. Now, the next section that we're going to kind of cover, I'm sure you are very familiar with. I know you've probably done them at some point in your math career. And it's not something that is necessarily covered on the AP exam anymore. However, it is very, very helpful in organizing information because sometimes they give you a lot of data and it can get overwhelming, it can get confusing. And so we like to use tree diagrams. And a tree diagram helps us display the outcomes of an experiment consisting of a series of outcomes. So, meaning one thing happens and then another thing happens. Could be two. Most of the time it is two. Could branch off to three. I would not expect anything more than that on the AP exam. So, example 3. YouTube is a popular destination on the internet for video sharing. About 27% of adult internet users are 18 to 29 years old, another 45% are 30 to 49, and the remaining 28% are 50 and over. A study found 70% of internet users aged 18 to 29 have visited YouTube, 51% aged 30 to 49, and 26% of those 50 and over. Draw a tree diagram to represent this situation. So we have two pieces of information. We have age group, and whether or not they have visited YouTube. So you have to the hardest thing I think students have with this is deciding what comes first. So generally you want to look at what's the overall separation of your groups. And it's not going to be 80% of the population visits YouTube, 20% does not. We first divided everyone into age groups. So that's what I'm going to do in my tree diagram. I'm going to divide my three groups based on the given percentages or decimals. Yeah, percentages. I had 18 to 29, and they said 27%, 18 to 29. So that's what I have going there. They said 45% are 30 to 49 and 28% are 50 and over. That takes care of my first couple branches of data. Then, once I have everyone separated into age groups, I then ask them, did you visit YouTube? Did you not? So for my 18 to 29, it said 70% did, which means that 30% did not. Oops, there's all my numbers together. Same thing for my 30 to 49. It says 51% did, and that means that 49% did not. For my 50s and over, it says 26% did, which means 74% did not. Now, in previous years, they may have asked you to construct a tree diagram based on data. They probably will not do that anymore because it's no longer in the curriculum. However, they will accept this as supporting work for probabilities. So if you're a person who wants to avoid using formulas at all costs and it's data that can be organized into a tree diagram, you can use this to support your answer and get credit for your work. A lot of the times as we go into probability, a naked answer, meaning an answer with no support, typically will not get you full credit. They want to see where your thought process is coming from. So, part A, what is the probability that this person is 18 to 29 and they visit YouTube? So, on a tree diagram, when I'm trying to get a probability, you have to remember that typically if I'm doing an and statement, an intersection, we're going to multiply both branches because both things have to occur in order for us to end up with this collected individual. So in order for me to have someone who's 18 to 29, I have to go down this branch. And then if they have to visit YouTube, I have to go down the 70% branch. So the probability of 18 to 29 and visits YouTube is going to be 0.27 times 0.7, which is equal to 0.189, which I was going to go in and say not plus, because you have to think rationally. If I were to add these two things together, that would give me 97% chance. I can't go in and say, I have a 97% chance out of all of these options of this occurring. Sometimes that does happen, but it makes a little bit more sense for me to have, there's a 1.89% chance of me selecting a person like this. given all of these different options, especially with how high the 30 to 49% is. Kind of reason through your answers if you're ever really unsure. So, anytime you want one of these outcomes at the very end, you need to multiply to get there. Otherwise, you are not calculating the correct value. So, what is the probability that this person has visited YouTube? All we want is just that they ended up at YouTube. So, what we're going to have to do is there's three options. They are 18 to 29 and they visit YouTube, they're 30 to 49 and they visit YouTube, or they're 50 plus and they visit YouTube. And remember, like I said, for the intersection, in order to end up at one of these ending branches, you have to follow the entire path. You have to go to each group specifically, and then within each group, you have to go the path of visiting YouTube. Now, this is an instance where we're going to add up those probabilities. So, probability of visiting YouTube, I'm going to take 0.27 times 0.7. That's going to take me down my first path. Add it to 0.45 times 0.51. That gives me my second path. And then add it to 0.28 times 0.26, which is going to give me my third path. And it's going to give me my total of 0.4913. And even when you are doing these joint probabilities, these conditional statements, any of this, you should still have that basic rule of probabilities applying. Everything has to be between 0 and 1. All of your totals cannot exceed 1. All of that still applies even in these conditional kind of settings. So for part C, we want to find, given that this person has visited YouTube, what is the probability that he or she is aged 30 to 49? So I have a given statement, given that they have visited YouTube. So I'm going to have, given that the person visits YouTube, what's the probability that he or she is aged 30 to 49? So I'm just going to do this based off of our formula. So I have my visits YouTube. They're going to be in the denominator because it's the given statement. And I want to find the intersection of 30 to 49 and visits YouTube. So if I want to find a person who's 30 to 49 and they visit YouTube, all I have to do is go down that branch. 30 to 49 visits YouTube, and I have to multiply those two things together. And the nice thing about this question, which happens a lot on the AP exam, we've already found the probability that they visit YouTube. We did that in part B, 0.4913, which gives me 0.4671. And I will say, more often than not, the AP exam does this. They have you calculate probabilities that you're going to use in the future. So make sure you're always aware of what you've already calculated, because it's going to help you save some time in the long run. Because yes, I could go back in and recalculate this, but why do that when it's already taken care of in part B? And the nice thing about the AP exam is they will grade your work through. So say for instance you happen to get it wrong in part B, that does not mean they will count it off here. They will take your wrong answer and just for the next part, if you're using it continuously, they will give you credit. It's a really nice thing because they won't just stop and be like, everything's wrong and not give you anything for your work, even though everything else could methodically be correct. And the last things we're going to cover for today, again, this is kind of a refresher jumble of things you've seen in some way or another in math. We have some counting principles. Tree diagrams tell us how many possible outcomes there are. They help us list those individuals and organize. However, sometimes you're only interested in the number of different outcomes created by a series of events. So we can use the multiplication rule of counting. If there are n possible outcomes and m possible outcomes, all you have to do is multiply the number of potential events to get your total number of combinations. So, for instance, we have McDonald's. There's 15 different sandwich options, and we have 3 different size options for fries, 3 different size options for drinks. How many different meals can be ordered with these options? All we have to do is take those 3 values, multiply them together, and that's going to give us the number of combinations we could have. 15 times 3 times 3. And sometimes we consider items where the order of arrangements is important. So in McDonald's example, it did not matter what I ordered first. I was still going to end up with the same collection of things. However, sometimes your options, your outcomes changes based on what you select. So a common example that often comes up is you're at a dinner party. You're at a dinner party with 4 friends. So there's 5 of you total. You approach the table and you see that it has 5 seats. So how many ways can the 5 of you seat yourselves in the chairs? Well, if you take a seat, there's only 4 chairs left. So that number is going to continue to decrease as you assign seats. So rather than doing 5 times 5 times 5 times 5 times 5, now we're doing 5 times 4 times 3 times 2 times 1, because the seats start to remove themselves as a person is seated there. So that gives me 120 different seating arrangements, and we often refer to this as a factorial. 5 factorial is equivalent to 5 times 4 times 3 times 2 times 1. If it was 6 factorial, we'd start at 6. 6, 5, 4, 3, 2, 1. Now, we're not going to get heavily into combinations and permutations because, again, it's not something they assess on the AP exam anymore, but we will talk about it a little bit once we get to binomial and geometric models. Now, kind of piggybacking off of that idea of having changes being made once you've done selection, we do have the possibility of dealing with things that matter if you replace something or if you do not. So, sometimes the probability is affected based on what has already happened. Occurrences like this often happen without replacement. This is going to be another way to calculate a conditional probability. So, this is a version of conditional probabilities. So when it can be selected more than one time, we are sampling with replacement. If it can only be selected one time, we are selecting without replacement. So an example, your dresser drawer is filled with 6 blue socks, 10 gray socks, and 4 black socks, unpaired and mixed up. One dark morning, you pull 2 socks from the drawer without replacement, meaning you don't put it back. What is the probability that both socks match? So I want the probability that both socks are matching. Well, in order for them to match, it has to be blue and blue, gray and gray, black and black. And I'm going to go through and I'm going to add those probabilities together, similarly to what I did with my YouTube people, for the people who visited YouTube in our previous example. Now, for the probability of blue and blue, first I have to total up my number of socks. So I need to add 16 plus 10 plus 4. So there's 20 socks in the drawer total. So for blue, my first chance of picking it is going to be 6 out of 20. But once that occurs, I'm taking away one sock from the drawer entirely. So for my second blue, it would be 5 out of 19. Plus gray, 10 out of 20. If I took one away, it'd be 9 out of 19. And then for black, it would be 4 out of 20 times taking one away, 3 out of 19, which when I multiply all of these together, I get 0.3474. So basically, you're adjusting the probability based on the given condition, based on the fact that you first selected this particular color of socks. That's going to change not only the denominator, but it also alters the numerator as well, because now that one blue sock is no longer in the drawer.